Well, hello everybody. In this screencast, we're going to spend about 10 minutes or so talking about basic terminology surrounding functions. What do you need to know about functions? So let's go right to the definition. A function from a set D to a set Y is a rule that assigns a unique element f of x in Y to each element x of D. This is a standard definition. You can reword it in a couple of ways, but they're really the same definition no matter how you slice it. Some things I should point out from here. A function is a rule, which often means it is an equation. Sometimes functions are expressed as tables of values. Sometimes functions are expressed in picture form. Sometimes functions are expressed in verbal form. And we will hit all of those as a class. But the important thing to know is that a function is a rule. Also important to know, this set D is what we call the domain. The domain is the set of all possible x values. Now that choice D is pretty standard. It's domain. It's the set of all possible x values. You are used to that from previous work with functions. This set is called the codomain. The codomain is the set of all possible y values. Now, sometimes all of the y values get mapped to. Other times not, which is why you are also familiar with this word called range. The range is the set of all y values that are mapped to by an x value. That is to say, if a y value is in the range, there is actually a point on the graph of the function that has that y value attached to it. And a hugely big word in the definition is the idea of uniqueness. When we send x's to y's, we do so in a unique way. So if here's my domain and here's my codomain, if I have 2 points in the domain and 2 in the range, it's okay to send both x's to the same y. That's legit. It is not okay to send one x to 2 different y's. That is not okay. Okay? Okay. So you are probably familiar. Oh, let's go black. You're probably familiar with taking a look at graphs and guessing what their domains and ranges are. This will be the point -3, 1. This will be the point 3, -1. Looking for domain and range, and it appears that the domain, all of these x values appear to be used, and so we would argue that the domain runs from -infinity to infinity. That's interval notation. It is also known as the set of all x such that x is a real number. The range appears to go from -1 up to +1. And since -1 and 1 are included, you get the square brackets there. This is the set of all y such that -1 is less than or equal to y, which is less than or equal to 1. Interval notation is the one we prefer. It takes up less space in most math textbooks, and we are nothing if not conservative on our spacing. If you have a problem with domain and range, it is sometimes helpful to imagine lights shining from infinity and from -infinity, where this function casts a shadow on the x-axis. The shadow, where the shadow is cast, tells you what the domain is, and similarly for range, we shine a flashlight this way and this way, and there's shadow cast in here, and where that shadow is cast is the range. There is some standard functions we should consider. For example, we should consider the absolute value of x. It's a physical function. It's fun to play at the absolute value of x MCA. This is the absolute value of x. We could talk about its domain and range. Not terribly difficult to do that. The domain, again, all x values appear to be good, and that will be the case most of the time. The range, there are no negative y values. 0 appears to be the smallest y value, and we shoot up from there. So 0 to infinity is your range. Similarly, this is the graph of y equals radical 2 minus x. If that's the graph of radical 2 minus x, think for a moment what could be the domain and the range of this function. Don't be afraid to hit the pause button. Make sure you've got it. Okay, so the domain, that all the x values, all these x values are good, 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 not good anymore. Where did they stop being good? Right here, where x appears to be 2. So the domain goes from negative infinity to 2. 2 is included. The range appears to be the same as the range for the absolute value function, so we're okay. Couple of nifty things to remember with respect to radical functions. You can't get a negative number out of a radical function unless there's a little dash in the front here. So this will be your standard range for a radical function. The radicand has to be non-negative because we don't deal with imaginary numbers in this course, and there was much rejoicing. So 2 minus x has to be greater than or equal to 0, which means that x has to be less than or equal to 2. Oh, look, x has to be less than or equal to 2. Okay? Okay. A couple of things we should know, working definitions. If f of x2 is greater than f of x1 when x1 is less than x2 on some interval I, then f is increasing on I. What? What? Okay, picture time. Okay, so here's my axes, and oh gosh, this will be x1, and maybe x2 is over here. And all I know is that f of x2 is greater than f of x1. That's all I know. F of x2 is greater than f of x1. But now that's true no matter what we pick for x1 and x2. So if this is the x2, then it has to have a y value higher than this one, but it could be x1 to this x2, so it has to be lower than there, so maybe it's over here. And if that's the case all the way across the interval, then we say that f is increasing on that interval. So that almost makes sense, and it's a little bit more rigorous than the function goes up. Yeah, what the heck does that mean? Similarly, if here's x1 and here's x2, and f of x2 is less than f of x1. So whatever f of x1 is, f of x2 is less than that, and if that happens for all combinations of x1 and x2, then the function is decreasing on the interval I. So that almost makes sense if you think about it. And these are things that you should have been exposed to. We include a little bit more rigor in this course. Definition that will be helpful to you, and a couple of pictures to illustrate. If f of negative x is equal to f of x for all x, then f is even. So what does it mean to be even? Well, it means that whatever f of this value is, f of that, so x, negative x, has to be the same. So you get the same y value. Whatever f is here, it has to be there. And so you get a function that is even. Even functions have y-axis symmetry. Even functions have y-axis symmetry. Draw yourself a few graphs with y-axis symmetry, come up with their equations, and you'll see why we call those functions even. Even. It's a nice thing to think about. Similarly, if f of negative x is the negative of f of x, so whatever the y value is here, at this x value, I go to its opposite x value and I get the negative of that. If that happens, then we get what's called an odd function. Odd functions have origin symmetry. Origin symmetry, functions like x cubed. So you can think for a moment about why we might call those functions odd. Interestingly enough, let's talk about some of my favorite evens and odds. Interestingly enough, let's take a look at one of my favorite even functions of all time. Do you recognize it? Gosh, I hope so. Now, you're thinking, hey, that doesn't have any even powers, but by the end of Calc 2, by the end of your study in single variable calculus, you will learn that this can be expressed as an infinitely long polynomial, all of whose powers are even. And, well, let's talk about the other favorite function of all time. Let's talk about the sine curve. The sine curve is odd. It has origin symmetry. But you will learn by the end of your second semester of calculus that that function can be expressed as an infinitely long polynomial, all of whose powers are odd. So the definition works, and the names have meaning. Things you should file away. Definitions work. Words have meanings. Excellent. Okay, so that's a brief intro to functions. Glad to have you along.